So I'm going to be talking about some new eigenvalue bounds we found out for the independence and chromatic number of powers of graphs. And I will define in a second what it is. First, let me give you a bit of background on the problem. Well, everybody knows what the spectrum of a graph is. I'm going to be talking about the adjacency spectrum in this talk. So just to be clear, I represent this adjacency matrix of the Petersen graph, which also represents the Sagrada Familia, because I'm originally from Barcelona. But what I want to remark here is that I'm going to be denoting the spectrum of a graph with two different notations. I'm going to be denoting lambdas when we don't include multiplicities, when we include repeated eigenvalues, and thetas to the subscript m when I consider only distinct eigenvalues of a graph. Okay? This is important because sometimes we use one or another notation depending on the bound. Okay. Let me now introduce what the graph power of a graph is. I believe this concept was introduced in 2002 by Mohar and Alon in a paper about the chromatic number of a graph power. So basically, given a graph, the k power of a graph is just formed by adding all the edges which are at distance smaller or equal than k. So if G is, for example, a cycle graph, G to the power of 2 would be this graph. You just add these extra edges for pairs of vertices at distance 1 or 2. For 3 gets denser, and for 4 obviously even more. Okay, so this is the definition of graph power. On the other side, I'm going to be talking about a generalization, an extension of the independence number of a graph. Everybody knows what the independence number is, but the k-independence number, maybe you didn't hear about it, is just the maximum size of a set of vertices which are at pairwise distance greater than k. Okay, so it's a natural extension actually of the classical parameter. And this is very important remark because we will use it towards the top. Like the k-independent number of a graph is just the independence number of the graph power. Okay, so there are many things that can be computed very quickly for the k-independence number, but not all, as we will see in this talk. So in particular, alpha 0 is just the number of vertices of the graph. Alpha 1 is independence number of a graph, the classical parameter. Okay, so for example, I can ask you, like, what is the two independence number of the dodecahedral graph? And in this particular example is 4. I gave you the solution here. However, in general, is obvious, like this is going to be NP-hard parameter to compute. I think someone is drawing on the screen. So the k-independence number is a NP-complete parameter to compute for general graphs. This was shown by Cohn and Zhao in '93. They also show a bit later that this problem actually remains NP-complete when we consider regular bipartite graphs for certain cases. And from the approximation algorithm's point of view, or from the algorithmic point of view, there is also some result which presents an heuristic-based algorithm for calculating two independence numbers. So in general, what I want to show you with this slide is that this is a hard problem. People from the algorithmic field have been trying to approach it, but yeah, okay. There is only an heuristic out there, so it's not very optimistic somehow. From the more graph theoretic point of view, previous work on this parameter has been done by Firby and Haviland in '97. They provide a sharp upper bound on the k-independence number for a connected graph. Also, Fioli in '97 provides some the first eigenvalue bound actually for alpha k by using the so-called alternating polynomial. I will define later on what they are or how they are calculating. And there is also a paper from 2005 by Bayes, Duck, Worth, and Tito, who also provide upper bounds which are sharp in some instances for random regular graphs for that parameter. Someone has any question? Okay. Let me continue. So there are more bounds. Recently, there has been some work on this parameter, this graph parameter, by Suil O, Shi, and Talqui, who also provide some algebraic, in this case, sharp bounds for the k-independence number of a regular graph. Also in 2020, other bounds appear for the two independence number of a tree. And recently, the k-independence number has been connected to certain beams function of a connected graph. Okay? Beams function is just like, instead of considering the discrete version of a graph, they consider that an edge is a set of points, and then they impose the distance constraint on this set of points which form an edge, instead of just considering the vertices, as we normally do. Okay, this parameter is also related to coding theory. It's not very hard to see that codes are actually k-independent sets in certain Hamming graphs, but in the hypercube, for example. And also there has been recently work by Fiol, who show that certain spectral upper bound on the k-independence number can be used to show non-existence of certain perfect codes attaining the Hamming bound in a particular family of graphs, in this case, the odd graphs. This parameter is also related to other combinatorial parameters, for example, to the average distance of a graph. So it's just the definition you have in mind, like you take the distance between any two pair of vertices and then you divide by n choose 2. And this Firby and Haviland actually provide some sharp lower bounds for the k-independent number in terms of the average distance. Well, actually it should be upper bounds, sorry, that's my typo. And then also there is a work by Chang, Delorme, and Solé, who introduced a parameter called the k-diameter of a graph, which basically extends the diameter definition, the classical diameter definition. And this parameter is also kind of related to the k-independence number. Okay, I also promised to talk about chromatic number. So let me define what is the k-distance chromatic number. The k-distance chromatic number is just the chromatic number of the kth power graph. Therefore, it's easy to see that k-independence, upper bounds on the k-independence number provide lower bounds on the k-distance chromatic number and the other way around, right? So we're going to be talking quite indifferently between alpha k or this gk, okay? Where is the motivation for this gk coming from? This comes from a specific coloring problem, which was first posed in 2002 by Alon and Mohar, who asked the audience the following question. They were wondering what is the largest possible value of the chromatic number of the graph power, okay, among all the graphs with certain maximum degree and girth at least a certain number, fixed girth. Okay, this for K1 is a very well-known problem by Bising, which was settled asymptotically by Johansson in '96 using the probabilistic method. The case 2 was actually settled also, I think, probabilistically by Alon and Mohar in the paper where they posed a question, actually, in 2002. And there are other general bounds for K by Alon and Mohar, Kang and Pirot, and Kang and Pirot. So Kang and the students were also working on this problem for some time. Okay. So our goal, I mean, not only trying to provide a bound for the previous question by Alon and Mohar, but our general goal of this talk is to extend two classical spectral bounds for the independence number of a graph. So the first bound we are aiming to extend is the inertia bound by Svetkovic, 72, which is a very simple cute bound that tells you that the independence number of a graph is upper bounded by the maximum, the minimum between the number of positive eigenvalues or the number of negative eigenvalues. And the second bound we want to extend is the Hoffman ratio bound, which is an unpublished result. And this bound depends on the spectrum of a graph as well. So, well, you have seen this bound before probably, and it's known when it's tight, actually. You can characterize equality of the bound. And actually it's important to remark that this bound was first found by Del Sartre, who provided it only for stronger regular graphs, and it was Hoffman who extended to regular graphs. Let me give you now a bit of motivation. Why do we care about alpha k? Why do we want to study this k-independence number of a graph? Because actually alpha k is just the independence number of the graph power, right? However, it's not even known that some of the parameters of gk, if they depend or not, if they are related or not to the parameters of g, the original graph, right? So for example, in particular, it's not known how the spectrum of gk and g in general relate. In some instances, we know how it does, but not always, right? So therefore, in general, we cannot just apply the inertial ratio bound to the graph power. This is why we want to provide bounds which only depend on the parameters, in this case, on the spectrum of the original graph and not on the power graph. Okay, this is what we're going to be doing. Okay, and the main tool is basically interlacing, as you can suspect, because the original proofs also use interlacing. So we have that two sequences of number interlace each other if this set of inequalities hold. And this is the graphical visualization of interlacing. When the case of the smallest sequence, the shorter sequence has n-1 elements, it's just giving the name of the interlacing, right? So in particular, for us, the sequences of real numbers are just eigenvalues of matrices, A and B. And there are two cases of eigenvalue interlacing we are going to be using. The first is when the matrix B, the smaller matrix, is just a principal submatrix of A. In that case, you can just apply Cauchy interlacing. This is very well-known results, the classical interlacing. And the second case of eigenvalue interlacing, maybe a bit less known, is by when B, the smaller matrix, is just the so-called quotient matrix, which contains in each entry the average row sum of the blocks in which you partition your original matrix, A, the big matrix. And then we have this result by Hammers in his thesis, who proved that the quotient matrix of a graph, its eigenvalues actually interlace the eigenvalues of the original large matrix that you partition into blocks, not necessarily symmetric. Okay? So the first situation, what I would like to study is when the spectrum of the power graph and the spectrum of the original graph are related. This case, we know that it happens only when the adjacency of the graph, the adjacency matrix of the graph power belongs to the algebra generated by the adjacency matrix of the original graph A. That is, or equivalently, there is a polynomial such that this equality holds, right? For instance, we have results that tell us this is the case when, for example, the graph is partially distance polynomial, right? And this was proved by Dalfo, Van Dam, Fiol, Garrig, and Horinsen in 2011. Okay, so this is the condition such that the spectrums are related, right? Now we want to see what can we say regarding this question by Alan and Mohar, which type of bound we could provide algebraically in this scenario when the spectrums are related. So there is this result in 2012 by Fiol, who actually provide an upper bound for a sum of polynomials evaluated in the largest eigenvalue. This sum of polynomials, I'm not giving you the definition, but is sum of polynomials of a family of polynomials called predistance polynomials, which is just a family of orthogonal polynomials with the classical properties, like having the holding the three-term recurrence of a distant regular graph, etc. And this is bounding above this polynomial evaluated in the largest eigenvalue. And he also characterized that equality in this bound holds if and only if there is this relationship between the spectrums of G and GK. So it means that there is polynomial QK evaluated in the adjacency matrix equals the identity plus the adjacency of the G to the power of K, okay? The adjacency matrix. So using this result, I'm presenting this result because using this result is almost straightforward, observing few more things that we can obtain algebraic bounds for that previous question, I suppose. So using the fact that QK has a property that evaluated in the largest eigenvalue is always larger or equal than evaluated in all the other eigenvalue, and using the inertia and ratio bounds, we can actually easily derive these lower bounds for GK, for the chromatic number of the graph power, which actually depend on the spectrum, basically, and yeah, on the existence of this polynomial Q, right? I mean, that's the main thing here. So let me give you a bit more intuition. The first bound is a type of inertia bound, and the second bound is a type of Hoffman bound. And now we're going to see how we can use these bounds, or how, in which situations we can calculate QK specifically, QK prime. And this -1 on QK prime is just because otherwise you don't have zeros in the main diagonal, so we had to shift, but that didn't change the result. Okay, so regarding this Alon and Mohar question, there are some papers, as I already mentioned, by Kang and his student, who provided lower and upper bounds on GK. But we were really interested in the lower bounds because they use some incidence construction in order to show that their bounds, lower bounds, were tight. In particular, they introduced a product called balanced bipartite product. Here I gave you an example because it's a bit technical to give this description of a product they provide. But basically, this product of two balanced bipartite graphs preserves balanced bipartiteness. And you can also calculate that is a regular graph, the resulting graph. And then this family of graphs actually turns out to satisfy our Hoffman-type bound when the spectrums are related for GK, okay? So that's one infinite family that thanks to this paper, we could also double check, and it's also tight for our bounds. But another case when the spectrums are related is when we have a graph which is regular with certain fixed Gerf and K for the alpha K, the Gerf -1/2, okay? We know that in this case, actually, this graph needs to be K partially distant regular with specific well-defined intersection numbers, as I indicate here. And therefore, one can easily calculate the specific expressions of the polynomials Q that we need in order to apply our bounds. Okay? is just a recurrence polynomials. And remember that Q were just the sum of the predistance polynomials. And we ran some set experiments just to see for which named set graphs this would be typed for our bound, for our Hoffman-type bound. Actually, we found some of them here. I put them on the table. Okay. So you see, like for fixed girth, you check the K, and then you compute the corresponding alpha K by using the bound, and then checking that actually gives the type value, the right value of the bound, of the value of alpha K. Okay, but in general, as you might suspect, the spectrums of GK and G are not related. So this is what I want to talk in the remaining of this talk, mostly. Okay. So let me first introduce the first work we did. This has a bit of historical background because we start little by little optimizing the bounds further and further. So the first paper on this was with Sevich and Michael Tate in 2016. The main tool we use is the most basic property we have in algebraic combinatorics, that the power of the adjacency matrix, the entries, count the number of walks of certain length from a vertex to another vertex. And let me present the main result, which is the first inertial type bound that we found. For that, we need two parameters. We need WK and capital W and non-capital W, the small w and big W, which will just look at, okay, you have a power matrix, you look at the main diagonal, and you take the smallest entry. That's the first parameter I put here on the screen, the minimum number of closed walks of length K over all the vertices. And the other one is just the maximum number of closed walks of fixed lengths over all the vertices. And then you can express, or you can prove that the K-independence number is upper bound by this expression, by the minimum of these cardinalities. Okay? The proof of this is not so surprising because it uses Cauchy interlacing as the first proof for a Svetkovic bound. But let me give you an idea. So assume that G has a K-independent set, we call it U, of size K-independence number. Then we also know that the matrix AK has a principal submatrix of size alpha K. So you put all the vertices corresponding to the independent set in the principal submatrix. And also we know that the diagonal entries will equal the number of closed walks of certain length, starting at one vertex and finishing at the same vertex, because we're in the main diagonal. So in particular, we're going to have something like this. And of course, one can just go and check the Eigenvalue interlacing inequalities, and actually Cauchy interlacing would lead you to the result. Okay? And obviously, for the K1 case, this gives you a Svetkovic bound. Okay? So, okay, the next thing we wanted to see is if we could provide an infinite family for this inertial type bound. And actually, we managed. It was a bit of a work, actually. So you start with a complete graph, and you remove an edge of the complete graph. We call this graph H. And then we make m copies of this graph with complete graphs minus one edge. We enumerate the vertices of the edge we just removed. And we attach an extra vertex X with a path of length K to the same vertex of the edge we remove, adjacent to the edge we remove. Okay, we call this is the graph actually that provides us a type bound for the inertial type bound. So this was a construction. I didn't give all details of the proof, but it was a constructive proof, basically, to control how the eigenvalues behave. The second result we show in that first paper is a Hoffman-type bound. So first we need to introduce some notation regarding a regular graph with some specific properties. So we are calling ND lambda graph. We are following Alon's notation here, where D is just the degree, so the largest eigenvalue. And then this D regularity of the graph guarantees that the largest magnitude of the largest eigenvalue actually is D. And then lambda is just the classical maximum between lambda 2, the second largest, and the smallest eigenvalue in absolute value. Okay? So it's related to expander graphs. You can already suspect it. So again, we need to redefine these parameters. Now it's slightly different because now we are considering the parameters W, but now we look at the maximum number of closed walks at length at most, instead of exactly K, at most K over all the vertices in the main diagonal. And then we were able to prove this type of Hoffman bound with Zhao and Tate. how do we prove it? The proof is slightly different than what you would expect, because one could think, okay, let's just try to do quotient matrix interlacing, which actually also works, as I will tell you later. But here what we did was like, okay, let's try to prove it using the expander mixing lemma, but we need a new version because we are talking about alpha k. So the first step would be try to extend the expander mixing lemma, which, yeah, well, I think everybody knows what it is. And then just consider an independent set of size alpha k. And in the expander mixing lemma, you are looking at the density of edges between two sets in your graph, S and T. So we consider that one of these vertex subsets is just a k-independent set. And then in the case of equality, we get the almost bounded we need, right? Okay, so this is the idea of the second proof, of the second bound. So when is this bound performing well? Because at first we were not able to find an infinite family with equality for this Hoffman type of bound, but we were able to test it on some sage graphs, as I will show later. But this bound should perform well when there is a good spectral gap because of the tools we're using actually and because of how it looks like. So it means like normally sparse graphs having very strong connectivity properties. And this is actually natural since the main tool we're using to prove it is just expander mixing lemma extended. Okay? In particular, obviously for K1, you get the Hoffman bound. How does our bound compare with previous bounds in the literature? I already told you Fiol had some bounds, Firby and Haviland had some bounds already, etc. So this Firby and Haviland bound is a bit more general because they don't assume regularity, while our Hoffman type of bound assumes regularity. However, under certain conditions, our bound performs better than theirs. So it's kind of like complementary in a way, for regular cases at least, for regular bounds. There are other bounds also. I mentioned a bound by Fiol using the so-called alternating polynomials. I think Fiol introduced these polynomials in his paper. Actually, they are the output of some optimization, some linear program method he uses. And they're just a specific family of polynomials that behaves very nicely. So, orthogonal polynomials. And then what he does is like, he finds these bounds that depend on pk, on these alternating polynomials. So obviously this pk comes from an optimization problem. This bound is quite good in general. So this is Fiol actually alternating, I think, like going up and down. And in general, obviously these bounds are incomparable. Like his bound optimized, given a spectrum, finds the best polynomial. So okay, so this is the scenario at the moment. So now you might think, what is next? What can you do better to improve these bounds actually? Well, we have been at the moment just talking about P of A, and we have been using P of A just being A to the power of K. So kth power of the adjacency matrix. And we have been looking at linear combinations of closed walks. So our bounds were just depending on these linear combinations of closed walks of a graph, which actually depends also on the spectrum. So in our particular bounds, we just prove that P of A is just A to the power of K, but you could consider like, yeah, but what happens if you take a different linear combination of adjacency matrices to the power, right? Can we push these bounds further? And obviously the answer is yes. Can we find other polynomials that improve these bounds? And the answer is indeed yes. So the second part was joint work with Michelangelo Fiol and Gabriel Coutinho from Brazil and Barcelona, respectively. So I'm not going to give the proof of this because it goes in the same line as the previous proofs I already did. So it's just a bit more notation-wise, a bit more heavy. We need to define the same parameters, these W's, counting the maximum number of closed walks of a fixed length, K. And then for any polynomial. So now we are not only looking at A to the power of K, but we are looking at any polynomial of the adjacency matrix, right? And then you can do the same story. Like you can write down an inertia type of bound and therefore generalize the previous result by us. And when is this bound actually interesting? Because it's a very generic bound for any graph, for any general graph. But this is only good if you can come up with a good choice of this P, right? Otherwise, it's not so useful bound. So later in the talk, we will see that we can optimize this bound. We can provide a method to calculate this polynomial, the best polynomial for each graph in practice. So in practice, this bound is useful. For the Hoffman type of bound, similar story, like you can also do it more generic. You don't only need to look at A to the power of K, but you can push the bound further by looking at any linear combination of adjacency powers. And then you obtain this bound. This bound can be shown also using quotient matrix interlacing. So the previous one, we used the expander mixing lemma for a to the power of k, but here actually you would do it using quotient matrix. It's just easier, quicker, and it gives the same bound, so it's nicer. So this is the remark I add here, like normally, or before we use expander mixing lemma, but we could just use quotient matrix interlacing to prove it. I'm not gonna give too much details of this, because the only thing you need to do is to calculate this corresponding quotient matrix of this polynomial evaluated in A in general. So it will depend on P, obviously, this quotient matrix. It's a 2 times 2 quotient matrix, so you can easily calculate its 2 eigenvalues depending on the polynomial. And then by Hammer's interlacing, you get the corresponding bound we provide, or we prove. Okay? And then, of course, we need some assumption, because otherwise you can get a 0 in the denominator. But that's the only thing. And this bound is for regular graphs, remember that. Okay. So this is an improvement of the previous Hoffman-type bound by Chow, Tate, and myself in 2016. It's a bit more generic, and it's sharp for some values of k, as we will see in the coming slides. And also in particular for k1, if you take the right polynomial, say px equals x, so just a, and the right parameters that we define for the bound, then we obtain Hoffman bound, okay, for a regular graph. For the case K2, actually, you can do almost by hand what is the best polynomial. You can find out almost by hand what is the best polynomial, and that's what we did in that paper, actually. But later on, we will provide methods that do it automatically. So I would say this is more like a, not a curiosity, but it's good to know that you can do it by hand for small values of k, but in general, like just better solve some optimization problem to find P. So the coming computational results I will show compare the best bounds, let's say, known for alpha k, for K2, for small k, okay? So we're gonna be looking at graphs which are in Sage, name it graphs in Sage, and then we're gonna be checking how our bound compares with Lovász bound, so this θ2, and how this compares also with our newer bound, more generic from 2019, and with the right, and then with the actual value of alpha 2. Right? I will tell you in a second why I'm comparing with Lovász theta bound. So this was the output. So you see our Hoffman-like bound from 2019. Let's look at that because it's a bit more generic. It's the best we have until now, we have seen until now. Compares quite favorable, quite good, performs quite decently if you compare with Lovász theta bound, which is the best to our knowledge at least for a bounding alpha k, upper bounding alpha k. And we run this, these graphs, we run this simulation for 1 minute only. So if it took larger than a minute, longer than a minute, we just put time here, okay? So I think in many cases it performs quite good, and it was quite quick also to calculate. So let me now remark why I'm comparing with Lovász theta function bound, okay? The Lovász theta function bound actually is known that provides an upper bound for the classical independence number of a graph. And because I told you, like the independence number is, the k-independence number is just independent number of the power graph, you also have that theta number of the power graph is the theta k, is the corresponding bound for alpha k, okay? So we have that, the theta k upper bounds our alpha k. That's why we are actually comparing with the Lovász theta function theta of the power graph. That's how we do the comparison in the previous table, okay? And remember that Lovász theta function just comes as an output of an SDP program. So yeah, Lovász theta bound upper bounds alpha k, but is also known, Lovász showed in 79, that the classical Hoffman bounds upper bounds Lovász theta number, or Lovász theta bound. So in general, theoretically, our bound, our Hoffman type bound obviously cannot beat Lovász theta number of the power graph, right? However, we notice that computing these eigenvalue bounds, which are based on mixed integer linear programs, which I will explain in a second, for small graphs at least, seems faster than solving an SDP program. Although complexity-wise, SDP is better than MILP, obviously, yeah? And as we saw in many cases, our bounds perform quite decently. So next question is like, what about further optimization? Can we do better even, or can we push that further? The answer is yes. How? as I already suggest, mention using mixed integer linear techniques to implement our eigenvalue bounds, and sometimes even assuming extra things on the graph, you can do it quicker. So you can always do it, but you can do it quicker if you assume extra properties on the graph. For example, partial walk regularities, I will explain. And this is a very recent work we just submit on arXiv with Fiol, Coutinho, which were previously also co-authors in the previous paper, and two students of us, Nogueira and Shane. Main questions then. Is the inertial-type bound and the Hoffman-type bound, are they possible to find? Are we able to find the best polynomial for a generic K? The answer is yes. So what we did in this work is like we optimize the inertial type of bound, okay? The one that generalizes or extends Svetkovich's inertia bound. So this was the bound we just saw, and we proved. How are we gonna optimize this? We are gonna write down a mixed integer linear program. We're gonna be using the spectrum of a graph which considers only distinct eigenvalues. So we are gonna have variables of size d plus 1. We are looking, our goal is to find this polynomial p of x. So our variables are actually the coefficients of such a polynomial which has at most degree k, but also this b, this binary vector of size d plus 1, which is going to be controlling the multiplicities of the graph, as we will see in a second. So for each vertex of the graph, we run one mixed integer linear program, and we find overall the best objective of all of them. Okay, let me give you a bit more details of what is this. So basically, what we want to do is we want to count how many times we have that p evaluated on any of the eigenvalues is larger or equal than this w parameter, okay? You can shift this parameter to be 0. That's also to make our life a bit easier, and it is still valid. So bj represents an index so that the polynomial evaluated in the eigenvalue is larger or equal than 0. And then the condition that I mark with this asterisk here is the one that implies such a thing, such a condition. So what we want to do is minimize the quantity of indices, the sum of these multiplicities of our eigenvalues, having that constraint of p of eigenvalues larger or equal than 0. Okay? We want to minimize that, how many times it happens. Okay, so the handicap of this optimization formulation or of this IP formulation is that you need to run one IP for each vertex, right? That's really not so handy, or it's quite slow at least. So how can you actually avoid running this MILP n times? You can do it by assuming that the graph is k partially walk regular. So if you know what a walk regular graph is, partially walk regular is not so surprising. It means that the number of closed walks of a given length, smaller or equal than k, only depends on this L, on the length, okay? So up to k, we have walk regularity somehow, up to length k. So in particular, every k partially walk regular graph is, every graph is actually k partially walk regular when it's 0, 1. And for k2, you just have a regular graph. Two regular graphs are two partially walk regular. So in that scenario, actually, you can reduce or rewrite a little bit this mixed integer linear program. And then you only need to run it once because all the vertices are going to have the same number of closed walks of length smaller or equal than k. Okay? So the first condition, the first constraint at least, can already be out. And I didn't write the reformulation of this for partially walk regular graphs, but it's not too hard to do. And then you can run it, for example, in some families of partially walk regular graphs. For example, for odd graphs, this MILP finds the best polynomials for upper bounding the k-independence number. There are other families of graphs for which we were also able to prove this in general, some family of Kelly graphs. But now you might wonder, why do we care about optimizing this inertial type of bound? Is there something extra besides just the fun of doing it and finding the best polynomials? Yes, there is some extra motivation, and the fact, or this motivation comes from the fact that this inertial type of bound is also valid to upper bound the quantum k-independence number of a graph. This is something we proved recently with two people from UK and US. And this would justify why we are using mixed integer linear program techniques in order to optimize, find the best polynomials to our inertial type of bound. Okay? So most of the quantum graph parameters are not known. What is the complexity to calculate them? If they can be calculated in finite time, is not known. Therefore, this would at least provide upper bounds for the number, for the parameter. And yeah, this comes, for example, from a paper by Mainsinska and Robertson in 2016, who proved that it's not known if the quantum information theory counterparts of the chromatic number and the independence number, if they are computable functions in finite time. And actually our bounds, our inertia type of bound and our Hoffman type of bound sandwich these parameters with the classical version. Okay. We also found an alternative inertial type of bound extending some previous results by Elphik and Bogyan. It looks a bit different than the inertial bound by Cvetkovic, although it has obviously the inertia round as well. And the main difference is like now we are not considering the polynomials, the evaluation of the polynomials which gives 0. Okay, we are only considering the positive cases and the negative cases on the bound. We also require a bit more restrictions here. Our previous inertial bound was generic for any graph. Here we need to assume K partially work regularity, and also that the trace is 0. Because, okay. So for this second or this alternative inertial type of bound, we also formulated the optimization problem to calculate it and see for which families of graphs this could be a good bound, or could find at least the best polynomials to calculate the bound. So the first constraint on the optimization problem is just that the trace of the polynomial on the matrix needs to be 0. The second constraint is counting how many times we have the polynomial evaluated in any eigenvalue larger or equal than 0. But here, notice this was a bit complicated to model for us at first because you need to control the zeros, in which cases P of lambdas are zeros. So this is modeled by the third constraint where, so we need extra variables as you see here. Before we only had B's, and now we have C's as well, binary vectors, right? Before we had B's, which had, they were vectors, binary vectors of length D plus 1, number of distinct eigenvalues. Now we have binary vectors which consider each single eigenvalue because we are also worried, we need to control how many of them evaluated give 0. Okay? So it's slightly different, the formulation. So basically with these 3 cases, we are controlling how many P's evaluated on lambdas are 0, how many are strictly positive and how many are strictly negative. And yeah, the remark is that now we have variables, n variables. So vectors of n coordinates. Okay, so what about the Hoffman type of bound? This was solved by Fioli this year as well, 2020. I think his paper is already published in linear algebra and applications. So he provides the optimization counterpart for the Hoffman type of bounds that we have seen, also using mixed integer linear programs, and the so-called, he introduced the so-called minor polynomials. So what he managed to find is like the best family of polynomials, or a very good family of polynomials, which in many cases gave the best polynomial for the Hoffman type of bound. For the inertial type of bound, that was not possible. We were not able to find a generic family of polynomials because I think that bound is more ad hoc also. It's like, yeah, well, we were not able to at least introduce a new family of polynomials. So you just calculate the best polynomial using the techniques I just showed, the optimization techniques. And finally, if time allows, I would like to say something about how this all relates to quantum graph parameter, the quantum version of the k-independence number. So let's continue with the inertial type of bound that we have seen, and let's see what this can be, what this says actually about the quantum counterpart in the k-independence number. This was recent joint work with Elphik and Bogyan. So let me maybe give you a bit of anecdote how this all started. I'm not a quantum person, I'm not a quantum expert at all, but I was invited to these analytical and combinatorial aspects of quantum information theory. This is a workshop that happened in Edinburgh last September when we could still meet. So it was one of the, I think it was the last workshop I actually could attend. And then of course, everybody mostly was talking about quantum graph parameters and bounds and stuff like that. So I was basically learning things there. And then at the same time, I saw on Archive a paper that caught my attention because they were providing an inertial upper bound for the quantum independence number of a graph, which was exactly the Cvetkovic bound that we extended. So I was wondering, like, can this also be done for the quantum k-independence number of a graph? the quantum counterpart of the k-independence number, the thing we have been working with. So this is a theorem these two people provide on arXiv. I had no idea about if this paper was published or not, or where was it, but I wrote them actually, and I asked, like, I think your bound also applies to this quantum k-independence number. So I'm going to explain a bit how that went. So the main question is, like, is this inertial type of bound also applicable, useful for the quantum k-independent number? And the answer is yes. Okay. The way to prove it is a bit different, because you don't use any more this Cauchy interlacing or anything I explained until now. So you need to go to the projective operators that they use in this quantum graph community. So we need a new definition. We need a preliminary definition, which is quite classical. Is the trace inner product of these two complex matrices, also known as the Hilbert-Smith inner product. It's just a trace of this X transpose conjugate Y. And then for the quantum independence number, there are several definitions out there. I had to read quite a bit because I'm not an expert on it. As I say, there are definitions using non-local games. There are definitions, more algebraic definitions, and more combinatorial definitions. And the one we wanted to, or the one that was better for us for the proof, was this Laurent and Piovesan definition that they introduced, or they proposed. Basically, first let me give you the definition of the quantum independence number, and then you will see how this naturally extends to the quantum k-independence number. So what you need is like a set of orthogonal projectors. So these matrices which are symmetric and idempotent. And then you need to guarantee certain conditions to happen for the independence number. The first condition is like just the sum of these projectors for each vertex equals the identity matrix. And the second and the third constraints or conditions are just orthogonality conditions, they call it, which means that there is some products that need to be zero. The important point to realize here is, like, because we are talking about the independence number, is like for each edge in that set, you need to guarantee that that product gives zero. So alpha q is defined using these d-dimensional projectors, and in particular, alpha corresponds with the projector of dimension 1. So just take like one number. So it's like this definition of quantum independence number extends the classical definition of the graph parameter, the independence number a bit. And Robertson, in his PhD thesis, observed that the quantum independence number actually upper bounds the independence number, the classical independence number. So the only thing one needs to observe is, like, the new definition you need is just to constrain, instead of making the product be zero, the orthogonality constraint be zero for any edge in the independence set. Now you need that this is zero when the distance is smaller or equal than k, right? We are going to be calling this parameter alpha kq. So the same thing, alpha kq is defined using d-dimensional projectors, and alpha k corresponds with the one dimension projector. A bit of motivation. What I understood is, like, in quantum information theory, this difference between the quantum k-independence number and independence number is a measure of the benefit of using something called quantum entanglement. Don't ask me exactly what that is, but it's apparently useful for the community. Also is useful because they don't know if these quantum counterparts of alpha and chi are computable functions in finite time. And also there has been quite a lot of literature on quantum graph parameters. So I just mentioned some papers I saw around here. And I think one of the first was the quantum chromatic number of a graph, with this set of authors, Cameron, Montanaro, Newman, Severini, and Winter. But there has been many people also looking at other quantum graph parameters and trying to find relationships with classical parameters, how big separation theorems and stuff like that. So basically, the inertial type of bounds that also upper bounds the quantum k parameter is the same that we found for the classical parameter. So that's actually very cute. The proof is totally different, but the bound is the same, still applies. The proof is different because you need somehow to translate this projective operator's definition to eigenvectors, and then somehow like rewrite things a bit differently. So it's a bit more involved than the inertial type of bound proof that we saw. But just keep in mind that alpha kq is upper bounded by the inertia bound. The reason I put this alpha kp is because for proving this result, it's easier to actually prove it for something called k projective packing number of a graph, which I'm not going to explain what it is here, but it's just something that it was easier for us to prove. And then we know that it upper bounds alpha KQ. Let me just finish telling you some consequences that this results that the inertial upper bounds the quantum k-independence number. Consequences that this could have for alpha Q and alpha. Well, the first one is like for the case of the polynomial being just the adjacency matrix. This is just the sandwich type of theorem that says that alpha is upper bound by alpha Q, and then in particular by the inertia bound by Edinburgh. We also saw at the very beginning of this talk that the inertia type of bound from myself, Chova, Tate, and myself, Continuum Fiol, is sharp for some infinite families of graphs. And because we have this sandwich type of thing here, we also know that these families of graphs are also providing sharp examples for this quantum version, quantum bound for the alpha KQ. Okay? And then in that case, we know that the classical parameter equals the quantum parameter. This is quite interesting. Okay? So as a corollary, we can say that for any graph for which the independence number equals the inertia bound, the classical inertia bound, then it has to hold that the quantum version of the independence number equals the classical version. So somehow you can calculate it in this scenario. This would be one condition that you can calculate the quantum parameter. And actually you can check this easily, and this is the case for several graphs in Satan list, like the ones I mentioned here. And another consequence comes from this question by Elsing and Gregory in 2010, who asked if such inertia bound by Edinburgh could also be applicable, or if there exists a real symmetric matrix W for every graph such that it holds with equality the inertia type of bound by Edinburgh. Elsing and Gregory demonstrate that this is actually true for all graphs up to 10 vertices and for vertex transitive graphs with 12 vertices. And actually recently Sinkovic proved that there is no such a real weighted matrix for which one is actually always tight or equal for this Paley 70 graph. But still, this leaves open the fact that we don't know if there is always a Hermitian matrix for which this quality is exact, is tight. And from our result with the upper bound on the quantum inertia bound, quantum k-independence inertia bound, we know that for every graph for which alpha is strictly smaller than the quantum counterpart, every graph holding that is going to be a counterexample for this question by Elsing and Gregory. Okay? So this is another consequence from our result. So let me now finish with some open problems. The first open problem comes from the quantum community because we have finished with that those results. So it would be interesting to find the graph, or people find it an interesting open problem, find the graph with the smallest number of vertices such that this is true. This separation happens between the classical parameter and the quantum parameter. These graphs should have at least 11 vertices, given some experimental results. And the smallest known graph has 24 vertices at the moment, if I'm not mistaken. Maybe something has happened recently, but I believe not. With this chromatic and independence number and this quantum independence number. And this was found by Laurent and Piovesan in 2015. And now other open problems, coming back to the spectral part of the talk, would be interesting to apply similar techniques or our methods, our mixed integer linear programs, to find other target polynomials, best polynomials in other graph families, or also for other values of k. I'm also very interested in this question, like try to find a relationship between these two bounds. The inertia bound and the Hoffman bound are both very interesting because they provide also proof for some important results in extrema combinatorics and for the Erdős-Corrado theorem. So it would be very nice to have somehow like one result unifying them. And we realize that in some instances, in some graph families, the minor polynomials that Fiol used to optimize the Hoffman type of bound are equivalent or are almost the same as the polynomials we obtain from our inertial type of bound optimization. So maybe via polynomials, we could be able to say something of how to unify these two famous bounds. Also, could we use these spectral bounds for the k-independence number to prove the non-existence of some perfect codes on some graph families, as Fiol did for odd graphs? Could we do it for other graph families? And also this result by Lenstra show that some mixed interlinear problems with fixed number of variables are polynomial solvable. So given a fixed n, could we find efficient algorithms to compute the best bounds with the MILPs we provide? So that was all from my side. Thank you for your attention. And please, if you have any question, go ahead.
Thank you very much, Aida. Thank you. It was great talk. Yeah. Yeah. Are there any questions to Aida, please? Well, actually, I have a lot of questions, but I'm not sure that I can ask you all of them right now. Well, the first one is the following. When you mentioned that your Hoffman-type bound performs well for expander, right? Yeah, but does this mean that it is also good for polygraphs?
Yeah.
Yeah. You mentioned about odd graphs, right?
Yeah.
Yeah. So in general, it can be used.
Yeah, I think so, but it's hard. I mean, it's always hard to find infinite families for which all of them performs well for that specific bound. But the idea would be to find the best polynomial for that infinite family. That would be the goal, using the techniques we provide.
I see.
They could be good candidates, yeah.
Mm-hmm. And you are quite optimistic for optimizing these bounds, right?
Yeah.
Yeah.
Yeah,
actually,
because
I like this approach when you use some optimization, spectral properties and some structural properties. So it gives very nice results. Very nice.
Yeah, combining fields is always nice.
Yeah, right. And actually, I also would like to know what do you think about this quantum independence number of a graph? I mean, what are other open problems in this area? You mentioned some of them, but yeah, from your point of view, what is one of the interesting?
I think people want to compute these quantum graph parameters in general. That's what I noticed. And because they cannot, or we don't know how to do it so far, like people are just trying to see this type of separation problems or characterizations when the classical parameter equals the quantum parameter. Because in those cases, then you can use the algebraic techniques, for example, or other bounds in order to get information for the quantum counterpart parameter. So my feeling is like there is no magic, or there is not so many people working on the algebraic approach to quantum graph parameters, but there is a lot to do there still, I think.
I see. And which kind of extra properties can be used in this case?
You mean from the graph, or?
Yeah, from the graph.
Oof, I'm not sure about that. Yeah, I should say, I don't know. Yeah, I never thought, yeah.
You just mentioned in your talk that we need to use some extra properties. So what does it mean, these extra properties?
No, but that was for the optimization. So, because of course, if you want to optimize a bound that is for general graphs, like in general, that might not give you maybe the best optimization procedure because it takes just too long. So then what we do is like, okay, let's focus on partially walk regular graphs, because at least we know that we need to run the optimization procedure once instead of n times, which was, so you sometimes, it's a trade-off between the optimization, the speed of the optimization, and the assumptions you do on your graph, right? Like, so it depends on the target graph you want to actually solve. But so if you want to solve graphs that are walk regular, for example, the optimization goes much faster, and then you can improve the formulation of the optimization. That's a good idea.